Hello atmospheric science students, Dr. Shragi here, and by now you have a working program that makes a map. And your map is probably pretty spectacularly colorful and also probably pretty spectacularly ugly. I mean, I have a program that I have made that we were using as our demonstration last time that looks something like this, and oh my goodness, setting aside the fact that it's a Technicolor nightmare. Another thing I really hate about this map is it spans the entire canvas. There's no place on here for a label, there's no place for anything, everything just goes right all the way to the edge. And that is not a very good looking map in my eyes. On the other hand, if I take, real quick here, I just want to show you what we're going to be doing today. If I go back over here to my assignment 11.c and compile it and run it. Okay, now admittedly on this program I have too big of a margin on the end, but you see how that's awfully nice? How line segments don't just extend all the way to the edge of the canvas, but they're only in a certain region of the canvas. In this case, it happens to be the region spanning this rectangle between, I think it's 0.2, 0.2, to this corner up here being 0.8, 0.8. But it doesn't really, I mean, that would be awfully small. But just this looks so much nicer. That is a very, very common problem in anything that you are rendering on a computer screen. That's called clipping. Clipping means I'm drawing stuff, but only actually put it on the screen if it's in a rectangle that I'm looking at. I mean, behind the scenes, clipping is happening all the time. It's why you can't see one window under the other, right? I mean, you only render the part that is inside the window. It's why when you bring up a browser, I don't even know what I've got here, with just some page in it, I mean, you're getting HTML instructions to draw the whole page that scrolls all the way down. Why don't you see the whole thing? It's because of the problem of clipping. The fact that it was clipped. It was made to just show part of the image. We need to get our maps to be clipped. And again, this is explained in more detail for you over in the textbook. Make sure you're keeping up with reading in the textbook. But I just wanted to kind of briefly go over this business of clipping with you using this PowerPoint here. I mean, here again, another map. This happens to be the state. I don't know if this is state or if this is WXP state database, but I mean, it looks lovely, but it also spans all the entire screen. There's no margins around the edge or whatever. I'd sure like there to be room for things like labels and so on. A map like this that is clipped, where there's just a region of the drawing canvas that's being used, sure is a lot more desirable. I mean, it just makes the plot look more professional. Well, let's think about this here. When we were going back to the gline command, when we were saying gline from x1, y1 to x2, y2, some combinations were outside of the window. It doesn't hurt anything to be drawing a line to coordinates outside of the unit square. The operating system is actually going to clip those commands, those line segments, so that they only show the part that is inside of the drawing canvas. That's clipping. Taking a little piece of the line segment and changing its line segment endpoints so that just the part inside of the window shows up. Now, for example, I made a little rectangle here. Let's say that is the part of the screen, of the graphics window, the canvas that I want to draw on. It's spanned by a rectangle that has one coordinate at A1, B1 and another coordinate at A2, B2. Okay, just sort of have some numbers there. All right. Well, here's a little line segment. Let's say for some reason I want to draw a line segment from x1, y1 to x2, b2. I'm sorry, x2, y2. Well, x2, y2 is not only outside of the window itself, but it's certainly outside of our clipping region. I really want it to do the math so that we can get just the part of the line segment, not that it ends when we get outside of the clipping region. Turns out this is a very common problem. All computer graphics, like 3D graphics, have to do this. That's how they decide what's behind and what's in front, when you have objects think in 3D. Clipping is surprisingly complicated. It is too much. I am not expecting you to write a clipping function here, because see, there's all these possibilities. I mean, look at each of these line segments on here. This one up here, I hope you can see my mouse, up here in kind of the top left corner. Well, that line segment has both of its endpoints outside of the window, and the little piece of the line that actually goes through the window doesn't actually go inside the clipping region at all. Here's another line segment, the one farthest to the right, they're not labeled on, if you can't see my mouse on here. Again, both of its endpoints are outside of the window, but a piece of the line segment actually does go through the clipping region. There's so many possibilities here. It is actually really complicated. But therefore, I'm going to give you the clipping function. This is not me being unrealistic or something like that. The truth of the matter is, everybody who's part of a team of scientists or whatever working on software is going to get code from everybody else. That's part of being on the team. This person's writing this code, this person's writing this code. In this case, I'm giving you the clipping code. You just need to implement it. Okay? In the same way that could happen to you. I mean, it happens to me all the time in my research. One of my colleagues gives me the code to do something, or I give the colleague code to do things, and that way we're not reinventing the wheel and so on, but you have to know how to actually implement the code. I'm giving you clip. Clip is a function. It's a void function. And what clip is going to do is it's going to change the values of x1, y1, and x2, y2 if needed to reflect how the endpoints need to change once the line segment has been clipped. It has 8 arguments, x1, y1, x2, and y2. And because x1, y1, and x2, y2 might change, they have ampersands in front of them. And then the last 4 arguments are the corners that describe your clipping region. That they aren't going to change, so you don't need the ampersands in front there. In case you haven't figured out, this ampersand thing really means like it's a function where the value might change. That's why you needed it in like scanf. The user is going to be changing the value of that variable inside of that function. That's why it needed the ampersand. After the function, the values of x1 and y1 might have been modified to reflect the new clipped line segment. And I'm giving it to you. It's called clipping.c. It's in my home directory. It is it's a function. Actually, there's a few functions in there. And inserted, I set down to handy.c. Some semesters we use that. I would call it metcalc.c. And I'm going to show you how to insert that those functions into metcalc.c the way you would anytime some colleague is sharing code with you. But before I do that, I want to show you what part of the code is. Part of what's inside of clipping.c is a bunch of lines that say pound define and then like a variable's name. I know it doesn't look like a variable's name, but, well, it's going to turn out not to be a variable. They're constants. But in this case, there's 1, 2, 3, 4, 5 constants, one called in, above, below, right, and left. They are part of how the clipping function works. They are constants, though. They're not going to change. So the author of clipping.c, who is not me, by the way, made them constants. They are defined. Forever in the program there, above is set to be the value 8, and below is equal to the value 4. If at any point in the program you tried to say above equals above plus 1, you'd get an error message because it'd be exactly the same thing as saying 8 equals 8 plus 1, which is mathematically impossible. This defines constants in here. See, then later in the code, there's pieces. I mean, we don't need to worry about exactly how clipping works. But, you know, code equals left, code equals right, code equals code plus below, code equals code plus above. We're using these constants. It wouldn't have had to have been constants. It could have been, the author could have just used variables, but constants are an awfully useful thing. I mean, it's often useful to have these constants. You don't declare them, you just up at the beginning of the program pound defined them. The constants cannot change inside the program, but they can be useful. I mean, values that are never going to change in your program, like northernmost, southernmost, easternmost, westernmost, it can be a useful thing to pound define them. At some later point in our program, we probably will actually do that, but at this stage it's not necessary. But I just wanted to kind of point that out because pound include and pound define are 2 examples of what are called precompiler directives. What's actually going on is when you compile these programs using GCC or GraphCC, what's actually happening is these things happen first. They are precompiler directives. First, it's going to go in and include those libraries. First, it's going to go through and define any place I see the word PI, I know that I'm going to replace that with whatever we define pi to be, 3.14159 or whatever. Every place that in the clipping function I see above, I'm going to change that to whatever the value of above was, 8 or whatever. So, constants, I'm not sure I was very articulate on this slide here, but you just give this constant a name and then set the name right there. And then literally the compiler goes through, before it converts your program to machine language, it literally will replace every place that says PI with 3.14159. Or if you pound define northernmost to be 40.0, then literally before it does any compiling and converting all this to machine language, it will literally go through and change all the values of northernmost to 40. This is particularly useful if you might then later change your mind and say, I'd rather have northernmost equal to something else. You just go to the top of the program where you have defined that constant and change it to something else. Alright, this is an awfully handy thing. Alright, in practice this is a very simple assignment once you have the map draw that you did in previously working. All you're going to do is produce a clipped map here. Let's actually take a look real quick here as to what that's going to entail. Let me minimize this here. Okay, I actually have already copied over from, let me do it again for you. I've actually copied over from shruggyj / I've copied over clipping.c to the current directory. Okay, and you can feel free to go look at it. It's a mess. I can tell you someday the story of the clipping.c function. I got it in a class a long time ago, and it's just so useful. We use it for a million things, and even though it's kind of an ugly code with no comments and stuff like, or just a few comments, etc., it works really well. And a handy place to put this is inside of metcalc.c. Now, I've already put it inside of my copy of metcalc.c, but that's an easy enough thing to fix. Let me just delete these lines up here. Okay, here's my metcalc.c. You can see up at the top is where I have my float, my transform latitude and longitude functions here. Alright, so now I have a copy of metcalc.c that does not contain the clipping function. I have a C file that contains this stuff. I want to just put that stuff into this file. Well, there's a nifty little trick in VI to do this. Oh, VI is so powerful, isn't it? :R, when you're in command mode, means read in another file. So like read in clipping.c will literally just read in clipping.c and put it where the cursor is right now. So literally, the contents of clipping.c just got added in to the top of this file ahead of wherever I was before. Put together this library. I mean, my copy of the library is getting to be how big? My copy is getting to be 354 lines long, and it's going to get longer. Wow, I mean, I just have all these handy little tools I'm just picking up along the way. Alright, so then later when I go into my program that is something I call mine assignment11.c, I have literally only added a couple lines to this program since drawing my map. When I had my program that drew the map but did it over the entire canvas, all I did is I made a copy of that and called it assignment11.c, and all I did is add this. I added a section where I'm clipping. Okay, so look where I am here. That might be important here. So I'm opening up my map file. While I'm not at the end of the map file, I'm reading in the map data, the latitudes and the longitudes. I'm transforming a longitude, transforming a latitude, transforming a longitude, transforming a latitude. I now have x1, y1, x2, y2. I just don't know if they're inside of my clipping region. So then I run my clipping function. Clip. It's got these ampersands in front of the x1s and the y1s because those are the values that are going to change, or at least might change. And then the next 4 arguments define the clipping region. Now this is an awfully big clipping region here, but we could have, made a different one, whatever. Well, once I've just done that, now the values of x1, y1, and x2, y2 might have changed, might not, depends on whether or not they needed to be clipped. And then I just drew the line. And so this line right here, that's all I added when drawing this database. It's almost too easy of an assignment. Alright, and then I just added the same thing here. I'm doing, what was this, the county database. And I just did the same thing. Before I did the G line to draw each line segment, inside of that loop, I clipped it. It's almost too easy. Anyway, very powerful tool, man. Everything from Toy Story to your software right here had to do clipping to make it so you could see where line segments end rather than going over each other and so on. Powerful, powerful tool. Alright, implement clipping. Show me how you can take pieces of code that somebody else gave you and pop them in and make them work. That is a powerful skill when you're being a scientist. And let me know if you have any questions. This has been Dr. John Schrage.